Dear participants, this first lecture will explore the societal and technological context in which industrial biotechnology operates at an important junction in human history. At this junction, mankind starts to realize that our continued existence on this planet requires drastic changes in how we produce food, fuels, and chemicals. We live in a unique, very short period in human history in which all material aspects of our life have become dependent on the abundant and cheap availability of fossil resources. In the case of oil, it's clear that this anomaly, which started just over a century ago, cannot last much longer than another century. By that time, easily recoverable oil will simply have run out. The abundant availability of fossil resources has supported and continues to support population growth. For billions of people, it has also enabled improvement of living standards. Simply doing without creates huge challenges. However, the need to do so is becoming ever clearer as we are confronted with the negative impacts of just a single century of unrestricted use of fossil resources. The abundant use of petrochemistry for production of non-biodegradable plastics and a wide range of novel-to-nature chemicals, so-called xenobiotics, confronts us with unprecedented pollution, from which no part of our planet is spared. But, as we are all aware, use of fossil resources has started to have a second and even larger impact on our planet. At first glance, the petrochemical carbon cycle shown in this slide shows deceptively sustainable. Sunlight is used to fix inorganic carbon in biomass. Geochemical processes then convert this biomass into coal, oil, and natural gas, which we mine, refine, and convert into fuels and other products. At the end of the life cycle of these fuels and other products, carbon dioxide is once again released. The problem with this cycle is that the time constants of the processes involved are so dramatically different. Filling the geological reservoirs literally takes eons, while we are in the process of emptying them just in a few centuries. Any engineer will point out that a cyclic process in which the compound processes operate at different rates will cause accumulation of an intermediate. And this is exactly what we see happening today with carbon dioxide in the atmosphere. And there we have mankind's greatest challenge for this century. A challenge that I sincerely hope many of you will devote your talents, your passion, and your energy to. We need to stop the rapid accumulation of carbon dioxide that is messing up global climate at an ever faster rate. To achieve this goal, we are in urgent need of innovative technologies to break out of this spiral. And you will be among the people provided the much needed ideas and solutions. To phrase this challenge in a slightly more scientific and less emotional way, we need to develop and implement large-scale, cost-effective processes that do not rely on fossil feedstocks. Instead, for carbon-containing products, the processes involved in their life cycles should have matching time constants, thereby enabling a net zero emission of carbon dioxide. Circularity is a key term in the development of such sustainable processes, which should generate chemicals and materials that we now make from fossil resources or functional equivalents thereof. In this context, circularity means that it should be possible to quantitatively funnel carbon dioxide, as well as other compounds that are released at the end of the life cycle of products, back into the production process. To achieve this goal, three main approaches can be distinguished: use of plant biomass as a feedstock, conversion of waste streams into products, and catalytic conversion of carbon dioxide to products or product precursors. As we will see throughout this course, use of plant biomass as the primary feedstock for product formation is right at the core of current industrial biotechnology. The growth cycle of many agricultural crops is shorter than 1 year. In theory, this can yield a closed carbon cycle in which carbon dioxide released at the end of the life cycle of a bio-based product can immediately be fixed again by next year's crop. As will be discussed in depth in later lectures, achieving this ideal situation meets with technological challenges and, moreover, needs careful integral analysis of processes and value chains. Instead of only relying on agriculture or forestry as a source of raw materials for industrial production, fixed carbon can also be intercepted within the life cycle of a product. Waste treatment systems, including wastewater treatment plants, are increasingly converted into resource recovery units, from which valuable elements and organic molecules can be derived. Examples of such biotechnological waste-to-product processes and important underlying concepts will be discussed later in this course. A third option to achieve zero-emission production of chemicals and materials is to tap into the 21st century energy transition. Today, our energy infrastructure is already increasingly dependent on carbon-neutral generation of electricity and will become even more so in the coming decades. Development of new biotechnological processes in which green electrons are used to convert carbon dioxide into organic platform molecules offers exciting options to eliminate greenhouse gas emissions. The drivers to invest in a sustainability transition now appear stronger than ever. We start to see and feel the real impacts, including the economic ones, of climate change. Solar and wind energy show that renewable technologies can be cost-effective. And at the same time, food security requires a massive move towards sustainable protein production, and many societies are once again confronted with the geopolitical risks of exclusive dependence on fossil resources. The drivers are there, it is up to us to contribute the required technological innovations. This first lecture exclusively focused on the context in which industrial biotechnology operates. A transition towards sustainability is the major driver for innovation and the main motivator for scientists active in this field. During the course, we will look much deeper into how industrial biotechnology connects to the three approaches for zero-emission production that were introduced in the previous slides. In the next unit, I will introduce industrial biotechnology, the main subject of this course. I hope to see you there.